Welcome back to the deep dive. We're here to really unpack the complex systems behind the internet services you use every day. Today, we're tackling a big one, cloud file storage.
That's right. We're going deep on the system design, the architecture for something like, well, Google Drive is our main model here. The goal is, to give you a real shortcut to understanding how these platforms actually manage your files, keep them synced, and handle just immense scale.
And when you say immense, you really mean it. We're designing for, what, 10 million daily active users?
10 million DAU, yeah.
Yeah.
With capacity planned for maybe 50 million signed-up users total.
Okay. And the core stuff we're focusing on.
It's the essentials. Upload, download, making sure file syncing is rock solid, handling file revisions, version history sharing controls,
Yeah.
and the notification system, which is super important for keeping everything snappy.
Right. But we need to be clear about what we're not covering today, yeah.
Definitely. We're specifically setting aside the whole real-time collaboration piece. Things like multiple people typing in a Google Doc at the exact same time.
Ah, the really tricky concurrency stuff.
Exactly. That's a whole other beast.
Yeah.
There's its own deep dive. Today's about the foundational storage and sync layer underneath all that.
Got it. So the hard requirements for that layer, what are the must-haves?
Okay, so needs to work on mobile and web clients, obviously. Got to accept any file type someone throws at it. Critically, files must be encrypted, both in transit and at rest. And we need to handle pretty big files, let's say up to 10 kilobit max per file.
Okay, standard stuff, but challenging at scale. But the environment, the sheer numbers, that's where it gets really interesting.
Yeah, the back of the envelope numbers really set the stage. Let's talk storage first. If you give just 10 gigabytes of free space, which is pretty common to those 50 million potential users,
Okay, 50 million times 10 gigs.
you immediately need 500 petabytes of total storage capacity, just allocated.
500 petabytes. Let's just pause on that for a second. For you listening, a petabyte is 1,000 terabytes. So 500 petabytes, that's half an exabyte.
It's a staggering amount of data. You need a system that can physically store that much and, crucially, retrieve any piece of it quickly.
It's like, what, all the photos ever taken or something crazy like that?
It's in that ballpark, yeah. And then there's the traffic hitting this storage.
Right, the uploads and downloads.
Let's be conservative. Assume those 10 million daily users upload just 2 files a day on average.
Okay, seems reasonable.
That works out to around 240 queries per second, QPS, just for uploads, continuously.
And that's the average, right? Peak load is worse.
Exactly. You always design for peak. So
Yeah.
you probably need to handle at least double that, maybe 480 QPS, maybe more, just for uploads, running 24/7 without breaking a sweat. That's the kind of environment this thing has to live in.
Wow. Okay, so that sets the scene. Massive scale, constant pressure.
So those numbers directly lead us to the non-functional requirements. These aren't user features like upload file. They're the fundamental qualities the system must have.
The promises the system makes.
Precisely. And for cloud storage, there are 4 big ones. First, and most important, reliability.
Cannot lose data, ever.
Non-negotiable. If you upload a file, it has to be there later. Data loss kills user trust instantly. It's the cardinal sin.
Yep. Lose my wedding photos, I'm gone. What's next?
Second, fast sync speed. Users expect changes to appear on their other devices almost instantly. If syncing takes minutes, well, people just won't use it.
Impatience is high these days.
Very. Third, bandwidth usage. Got to be super efficient here. Millions of users are on mobile, often with limited data plans. We can't just be sending huge files back and forth unnecessarily.
Especially with those 10 gigabit files.
Exactly. We need clever ways to minimize data transfer. And fourth, naturally, is scalability and high availability. The system needs to grow easily as usage increases, and it needs to stay up and running even if servers fail or data centers have issues.
Okay, so reliability, speed, efficiency, and uptime at scale. Makes sense. Now, it's tempting to jump straight to the complex distributed system that achieves all this, but the sources point out it doesn't start that way, does it?
No, never. It's crucial to understand the evolution. Think about day one. You might literally start with a single, pretty powerful server, maybe running Apache for the web stuff, a basic MySQL database for metadata.
Like file names, user and...
Yeah, exactly. And then just a big local hard drive, maybe 1 TB, partitioned into directories to store the actual files.
How were files identified back then?
Super simple. Each user gets their own directory, a unique namespace. The file's unique ID was basically just that user's directory name plus the file's path within it, like user123 documents report.docs.
Okay, that sounds almost quaint, but I can already hear the alarm bells ringing.
Oh yeah, the first inevitable crisis is the disk space full alert. You hit that 1 TB limit way faster than you think.
And the whole service grinds to a halt.
For everyone. Plus, even before that, the single MySQL database gets crushed by the read-write load. The single web server can't handle the QPS. It just falls over.
So the system forces you to scale out. What's the first emergency fix?
Usually database sharding. You have to split that single database across multiple machines.
Okay, how do you split it?
The most common way here is sharding based on usered. You basically say users AM go to database server 1, users NZ go to server 2, and so on.
Why userid? Why not like shard by file type or something?
Great question. It's about data locality. Most of the time, when a user interacts with the system listing their files, checking sync status, they only care about their own stuff.
So sharding by userid means most queries only need to hit one specific database server.
Exactly. It keeps related data together and avoids having to query across multiple database shards for a single user's request, which would be way slower.
Okay, sharding helps the database bottleneck, but you still have the actual files sitting on those local server hard drives. That feels risky.
Extremely risky.
Ah.
Even if you add more servers just for storage, you're now managing complex file systems, backups, worrying about disk failures, wiping out chunks of user data. It becomes unmanageable and dangerous.
So this is where external cloud storage comes in, like S3 or Google Cloud Storage.
Precisely. It's a critical pivot. You stop trying to manage the raw storage yourself and leverage the massive scale and expertise of a dedicated cloud provider.
What are the big advantages there? Why make that switch?
Several huge ones. You get industry-leading scalability. They handle the petabytes. You get incredible data durability. We're talking 99.999, like 11 nines of durability, meaning data loss is astronomically unlikely. Plus built-in security, high performance. You just can't build that yourself economically.
And a key part of that durability is how they store the data, right? The redundancy.
Absolutely. It relies on aggressive replication. First, there's same region replication. The provider automatically keeps multiple copies of your data within different facilities in the same geographic area. That protects against local failures, like a single server rack dying.
But what if the whole region has a problem, like a hurricane or major power outage?
That's why you also need cross-region replication. Your architecture needs to ensure that complete copies of the data are stored in geographically separate regions, say US East and US West.
So if one entire region goes offline, the data is still safe and accessible from the other region.
Exactly. It's your ultimate insurance policy for availability and durability, essential for a service like this.
Okay, robust storage, sorted. Now, how do clients, the apps on your phone or computer, actually talk to this system securely? You mentioned 3 main APIs.
Right, and all communication must use HTTPS for encryption in transit, and every request needs proper authentication, usually via tokens.
Makes sense. What's the first API? Upload.
Upload is the most complex. For small files, maybe under a few megabytes, a simple upload API is fine, just POSD the data. But for those big 10 gigabit files or for users on flaky mobile networks,
You need something more robust.
you need the resumable upload API. This is crucial for user experience. Nobody wants a 5 gigabit upload to fail at 99% and have to start over.
Definitely not. How does that resumable process actually work? Is it complicated?
It's a well-defined 3-step dance. Step 1. The client sends an initial request, basically saying, hey, I want to upload this big file. The server responds with a unique temporary URL specifically for this upload session.
Okay, like a dedicated upload endpoint.
Exactly. Step 2. The client starts sending the file data, usually in chunks, to that specific URL. The client also needs to keep track of how many bytes it's successfully sent.
So it knows where it left off if something goes wrong.
Precisely. Step 3. If the connection drops Wi-Fi blips, phone goes into a tunnel, the client can reconnect and use that same temporary URL to ask the server, hey, how much data did you get for this upload? The server responds, and the client resumes sending data from exactly where it left off.
Ah, very clever. Handles interruptions gracefully. What about the other 2 APIs? Download and getting file versions.
Much simpler, thankfully. Download is typically just a GET request with the file path. Often the server responds not with the file itself, but with another temporary signed URL that points directly to the file in cloud storage, like S3. This offloads the actual data transfer.
Okay. And getting revisions.
Also a GET request. You provide the file path and maybe a limit parameter, like give me the last 5 versions. The API returns the metadata for those historical versions. Again, probably with URLs to download them if needed. Keeps things efficient.
Okay, let's zoom out and look at the whole system now. We've got this distributed setup, web servers handling requests, A metadata database tracking everything, and the actual file storage in the cloud. How does it all connected?
The glue holding it together, right at the front door, is the load balancer.
What exactly does that do? Just spread traffic around.
It does that, but it's more sophisticated. First, it usually terminates the HTTPS connection, handling the encryption-decryption so the servers behind it don't have to. Second, it constantly runs health checks on all the downstream servers.
To make sure they're alive and responding.
Yep. And if a server fails a health check, the load balancer instantly stops sending traffic to it. That's key for high availability. And third, yes, it distributes the incoming requests evenly across the pool of healthy servers, usually the API servers.
You mentioned API servers. You called them stateless earlier. Why is being stateless such a big deal here?
Statelessness is huge for scalability and resilience. It means the API server handling your request doesn't store any information about your session or your previous requests locally.
So any API server can handle any request at any time.
Exactly. They're completely interchangeable. If one fails, the load balancer just sends your next request to another one, and it doesn't matter because there's no local state lost. It also means we can add or remove hundreds or thousands of API servers instantly based on traffic load. That elasticity is crucial.
Okay, so these stateless API servers,
Real.
what do they handle if not the actual file content?
They handle all the core logic and coordination, user authentication, managing user profiles, handling sharing permissions, and critically orchestrating all the updates to the metadata database. They're the brains controlling the flow, but they don't do the heavy lifting of moving the actual file bytes.
Right, the bytes go elsewhere. Let's talk about that metadata database. You said it's the central nervous system.
It really is. This database stores everything except the file content itself. User information, file names, folder structures, which blocks make up which file, version history, sharing permissions, pointers to where the actual blocks are stored in the cloud.
So it's just the descriptions in the map.
Exactly. The actual files live in S3 or equivalent. The database just tells the system about the files and where to find their pieces.
No, accessing this database constantly must be a bottleneck. I assume there's a big cache in front of it.
Absolutely. A massive metadata cache is essential for performance. Reading from memory cache is orders of magnitude faster than reading from disk database.
But wait, we talked about needing strong consistency. How does a cache fit with that? Caches can get out of date, right?
That's the million-dollar question. And you're right, it's a huge challenge. For a storage system, eventual consistency where different users might see slightly different versions for a short time is generally unacceptable. If I rename a file, you need to see that new name immediately.
So how do you guarantee that strong consistency, especially with a cache?
Two main strategies. First, the choice of the database itself. For the core metadata, you'd typically choose a relational database like PostgreSQL, MySQL, because they offer AC properties built in.
ACID, atomicity, consistency, isolation, durability. Can you quickly remind us what those mean in this context?
Sure. Atomicity. An operation like uploading a file and updating its metadata either completes entirely or fails entirely. No half-done states. Consistency. Ensures every transaction moves the database from one valid state to another, respecting all rules. Like a file always belongs to a user.
Okay, and isolation, durability.
Isolation. Concurrent operations don't interfere with each other. If two people try to rename the same file at once, isolation ensures the database handles it predictably, not corrupting the state. And durability. Once an operation is committed, it survives failures, like server restarts. Relational databases are designed for this.
But relational databases can be harder to scale horizontally than NoSQL databases, right? And they can be slower for writes because of locking?
True. It's a trade-off. We accept some scaling complexity and potential write latency to get those strong ACD guarantees, which are paramount for data integrity here.
Okay, so the database choice helps. What about the cache? How do you keep the cache consistent with the database?
Rigorous cache invalidation. This is critical. Whenever any data is written or updated in the master database, the system must immediately invalidate or update the corresponding entry in the cache.
So if I rename file.txt to report.pdf in the database,
The system instantly tells the cache, hey, whatever you have stored for file.txt is now garbage. Throw it away. The next time someone asks for that file's metadata, the cache won't have it. Cache miss. So it has to go back to the database, which now has the correct corrector, report.pdf info.
that sounds complex to implement reliably.
It is. Cache invalidation is notoriously tricky, but it's absolutely necessary to maintain strong consistency while still getting the speed benefits of the cache for reads.
Okay. Now we mentioned the API servers don't handle the heavy lifting of file bytes. Who does?
That brings us to the real workhorses for uploads, the block servers.
Block servers. What's their main job?
They sit between the client and the final cloud storage, like S3. Their core function revolves around block-level storage.
Meaning they break files up?
Exactly. Instead of treating, say, a 1 gigabit video file as one giant blob, the block server splits it into smaller, fixed-size chunks or blocks. Dropbox, for example, reportedly uses 4 MB blocks.
Okay, 4 MB chunks. What happens to each chunk?
Each block is treated as an independent piece of data, and crucially, each block gets a unique cryptographic hash calculated for it, usually SHA-256. This hash acts like a fingerprint for the block's content.
That hash seems important. We'll come back to why, I bet. But what else do the block servers do to these chunks before they hit S3?
3 key things, usually in this order: compression, encryption, and then the actual chunking splitting if the client didn't send it chunked already.
Compression first.
Makes sense. You want to compress the data to make it smaller before you encrypt it. Compression algorithms work best on predictable patterns, which encryption destroys. The type of compression depends on the file type, maybe gzip for text, but maybe nothing for a JPEG, which is already compressed.
And encryption.
Right. Usually strong encryption, like ES256, using keys managed securely by the backend system, not the client. This ensures the data stored in S3 is unreadable without the keys.
Okay, so block servers chunk, compress, encrypt, and hash. Why have this intermediate layer? Why not just upload straight to S3? We'll get to alternatives later, but what's the main benefit this enables?
The single biggest benefit, related to our non-functional requirements, is optimizing network bandwidth via Delta Sync.
Ah, the magic of only sending changes. How does block storage enable that?
It's all about those hashes. Imagine you have a 500 MB file made of many 4 MB blocks. You edit just a small part of it. When you save, the client or the block server recalculates the hashes for all the blocks in the new version of the file. It then compares these new hashes to the hashes of the blocks stored for the old version.
And it sees most of the hashes are identical.
Exactly. If only, say, blocks 2, 5, and 10 have different hashes, the system knows only those 3 blocks actually changed. So instead of uploading the entire 500 MB again,
It just uploads those 3 4 MB blocks?
precisely, just the delta of the change. This saves enormous amounts of bandwidth for the user and massive egress costs for the service provider. It's a cornerstone optimization enabled entirely by processing the file at the block level in these servers.
Okay, we've got the pieces. Load balancer, API servers, metadata, DB and cache, block servers, cloud storage. Let's walk through a typical upload flow.
Yeah.
Client 1 wants to upload a new file. What happens first?
It actually triggers 2 parallel flows, more or less. Let's call them the metadata flow and the content flow.
Okay, metadata flow first.
Client 1 sends an API request to the API servers. This request contains the metadata about the file, its name, maybe its size, type, where it should go.
Not the file itself yet.
Correct. The API server authenticates the user, validates the request, and then writes this preliminary metadata into the metadata database. Crucially, it sets the file status to something like pending upload,
Why pending?
because the actual file content hasn't arrived in storage yet. This status tells the system the file exists conceptually but isn't ready. And importantly, as soon as this pending record is created.
The notification service gets pinged.
Exactly. The API server notifies the notification service saying, hey, user X just started uploading file Y. This lets other connected clients know something is in progress.
Okay, that's the metadata side. What's happening in parallel with the file content?
That's the content flow. While the metadata is being processed, client 1 starts sending the actual file data, maybe chunk by chunk, directly to the block servers.
The workhorses.
Yep. The block servers receive the data, do their thing, chunking if needed, compressing, encrypting, calculating hashes for each block. Then they upload these processed encrypted blocks to the final cloud storage, like S3.
Okay, blocks are landing in S3. How does the system know when all the blocks for that file are safely stored and the upload is complete?
This usually involves a callback mechanism. Once cloud storage confirms that all expected blocks for a given file upload session are successfully received and ideally replicated.
It tells someone, job done.
Right. S3, or equivalent, triggers a completion notification or callback. This callback typically goes back to the API servers.
Okay.
The API server receives this upload complete signal, finds the corresponding file record in the metadata DB, the one marked pending, and updates its status to uploaded or available.
And then it notifies everyone else.
Yes. After the status is updated in the database, the API server tells the notification service again. Okay, file Y for user X is now fully uploaded and ready. This two-stage notification prevents clients from trying to download a file that isn't actually complete yet.
That makes sense. A decoupled flow for robustness. If the metadata update is slow, the content upload can still proceed.
Exactly. It avoids making the user wait for database locks before the potentially long upload can even start.
Okay, upload complete. File is available. Now, how does client 2 on maybe a different device find out about this new file? That's the notification service's job, right?
Absolutely. The notification service is the linchpin for fast synchronization. If client 2 is currently online and connected.
It gets a push notification.
Essentially, yes. The notification service sends a message saying, hey, something changed for user X. It might not contain the full details, just a trigger to check for updates.
What if client 2 is offline, like their laptop is closed?
Good point. The notification can't be delivered immediately. So the system needs to store these pending notifications. There's usually an offline backup queue or something similar specific to each user or device. When client 2 comes back online,
It checks that queue.
exactly, it connects, asks anything new for me, and pulls down the list of changes that happened while it was offline.
Okay, so client 2 gets notified either immediately or when it reconnects. What happens next for it to actually download the new file?
Once client 2 knows something changed, its first step is to ask the API servers for the latest metadata. What's new with file Y, or give me the latest state of this folder.
The API server queries the metadata DB.
Right. The database returns the current metadata for the file, which now includes the status uploaded and, critically, the list of blocks and their hashes and locations in S3 needed to reconstruct the latest version.
So client 2 gets the blueprint for the file.
Precisely. Client 2 then uses that blueprint to request the necessary blocks. Where does it request them from? Usually the block servers again.
Why not directly from S3? Didn't we say downloads often use signed URLs to S3?
Good catch. It could potentially go straight to S3 with signed URLs if the blocks didn't need decryption or decompression handled server side. But often the blocks in S3 are encrypted.
Ah, so the block server acts as the decryption point on the way out, too.
Yes, it often does. Client 2 requests specific blocks from the block servers. The block servers fetch the corresponding encrypted blocks from S3, decrypt them using the correct keys, potentially decompress them, and then send the plain data blocks back to client 2.
And client 2 receives these blocks and pieces the file back together locally.
Correct. It reconstructs the complete, updated file using the blocks it just downloaded. Sync complete.
Okay, that flow seems robust. But what happens if, say, user A and user B both modify the same shared file at roughly the same time, especially if one of them is offline for a bit? Conflicts seem inevitable.
They are. This is sync conflict resolution, a classic headache in distributed systems. There's no single perfect solution, but a common approach is relatively simple.
What's the rule?
The rule is often, the version whose metadata update is processed first by the metadata engine wins. Last write wins, essentially, based on server processing time.
Wait, process first. So if my change hits the server a microsecond after yours, my change loses, even if I started editing earlier.
Potentially, yes. It's defined by when the database write transaction for the metadata update successfully completes and releases its lock. It prioritizes consistency and speed over trying to figure out user intent or complex merging.
That feels a bit harsh. Why not try to merge the changes or look at timestamps?
Because that introduces immense complexity and risks violating strong consistency. Automatic merging is only feasible for certain file types, like plain text, and is prone to errors. Relying on client-side timestamps is unreliable, as clocks can be wrong or easily manipulated. Sticking to server transaction order wins is simpler, faster, and guarantees a single, consistent state on the server.
Okay, so my update loses the race. My local file is now different from the server's winning version. What happens on my client?
You get a sync conflict notification. The system detects that the version you tried to save is based on an older version than what's now current on the server.
And what does it show me?
It typically presents you with both versions. Your local copy, the one that lost, and the current server version, the one that won't. And it forces you to choose.
What are my choices?
Usually.
Yeah.
1. Keep your local version, effectively overriding the server's version, with yours in a new update. 2. Discard your local changes and accept the server's version. 3. Or sometimes it might save your local version as a new, separate, conflicted copy file, leaving the server version as is.
So the system punts the resolution back to the user because only the user knows which version is actually correct or how to merge them manually.
Exactly. It avoids automated guessing and potential data loss, putting the user in control of resolving the conflict.
All right. Let's circle back to that notification service. It's clearly vital for timely syncs and conflict alerts. The sources mentioned it uses long polling instead of WebSockets.
Right.
Why?
Yeah, this is an interesting technical choice. WebSockets give you a persistent two-way communication channel. Great for chat apps, real-time games, where data flows constantly in both directions.
But for file sync notifications.
The communication is mostly one-way. Server telling the client, hey, check for updates. It's also usually infrequent. Files don't change every second for most users, and there aren't bursts of data like in chat.
So a persistent WebSocket connection might be overkill.
Exactly. And potentially very resource-intensive at scale. Imagine maintaining millions, tens of millions of persistent TCP/IP connections open on your servers, even when no updates are happening. Each open socket consumes server memory and resources.
How does long polling avoid that? It still keeps a connection open, right?
It does, but differently. With long polling, the client makes a standard HTTP request to the server, basically asking anything new. The server doesn't respond immediately. It holds that request open.
Waiting for something to happen.
Right. It waits maybe for 30 seconds, 60 seconds, whatever the timeout is. If a file change does occur during that time, the server immediately sends the notification as a response, closing the connection.
And if nothing happens within the timeout?
The server sends back an empty response, maybe a no changes status, and closes the connection. In either case, as soon as the client gets a response, or times out, it immediately makes a new long poll request.
Ah, so the connection is only held open while actively waiting, and it closes frequently. That sounds less resource-intensive than a permanently open WebSocket.
Generally, yes. It reduces the burden of managing millions of truly persistent idle connections. While there's overhead in constantly reestablishing connections for this specific use case infrequent, server-to-client notifications, it often scales more efficiently in terms of server resources.
The source mentioned Dropbox handling over 1 million long poll connections per server. That's pretty impressive scaling.
Yeah, it shows that long polling, while maybe less modern than WebSockets, is a perfectly valid and highly scalable technique when the communication pattern fits, like it does here. Okay, let's talk efficiency, especially storage cost. We've got those 500 petabytes, plus potentially many versions of each file. That storage bill could be astronomical. How do we minimize it?
The block servers gave us a hint earlier with those hashes.
Exactly. The first major technique is data deduplication. Because we've broken files into small hashed blocks, like 4 MB, we can compare the hashes of all blocks across the entire system.
So if user A uploads a video and user B uploads the exact same video.
Or even if they upload different files that happen to contain some identical blocks, like common library files in software or standard image headers, if two blocks anywhere in the system have the same hash, we assume their content is identical.
And you only store that block once physically in S3.
Precisely. Even if thousands of different files across thousands of users reference that same block content, we store the physical data just one time. The metadata for each file simply points to that single shared physical block.
That must save a ton of space, especially with common files or duplicated content.
Huge savings. It dramatically reduces the actual physical storage footprint compared to the logical size of all user files combined.
Okay, deduplication helps. What else? We store file revisions, right? That must add up.
It does. So we need an intelligent data backup strategy, not just keeping every single change forever.
How do you manage that? Just delete old versions?
Partly. Two common tactics. First, a simple limit on the number of versions. Maybe we only keep the last 30 versions of a file. When version 31 is created, version 1 is automatically deleted.
Okay, a rolling window.
Right. But you can be smarter. The second tactic is keeping only valuable versions. Think about a document you edit intensely for an hour, with autosave happening every minute. Do you really need all 60 of those micro versions from 2 years ago?
Probably not. Maybe just the state at the end of the hour.
Exactly. The system might assign more value to versions spaced further apart in time, especially older ones. So it might keep all versions from the last day, but only one version per day for the previous week, one per week for the previous month, and maybe only one per month beyond that.
Ah, like an exponential back-off for version retention. Prioritizes recent changes, but thins out the distant history.
Exactly. It saves space while still providing good recovery points for recent mistakes and significant historical milestones.
Smart. Any other storage cost savers? What about files nobody touches for years?
That's the third technique, cold storage integration. Data identified as cold, meaning it hasn't been accessed for a long time, say 6 months or a year, can be automatically migrated to a much cheaper storage tier.
Like Amazon S3 Glacier or Google Cloud Archive?
Yep. These services offer dramatically lower storage costs per gigabyte, sometimes 90% cheaper or more. The trade-off is retrieval time. It might take minutes or even hours to get the data back, instead of milliseconds.
But for truly archived, rarely accessed files, that's a worthwhile trade-off for the cost savings.
Absolutely. For a system storing petabytes over many years, actively managing data temperature and moving cold data is essential for cost control.
Okay, efficiency covered. Let's switch to reliability under fire. Things will fail. How does the architecture handle failures in its key components? Starting at the front, the load balancer.
The load balancers are typically deployed in pairs or more. A primary handles traffic, while a secondary constantly monitors the primary using a heartbeat signal.
Like a little I'm alive ping.
Exactly. If the secondary stops receiving the heartbeat from the primary, it assumes the primary has failed. It then immediately takes over the primary's virtual IP address and starts handling traffic. Failover is usually very fast, almost seamless.
What about the block servers? If one dies mid-upload while it's compressing and encrypting chunks?
The work needs to be picked up by another block server. This usually relies on a persistent job queue. When a block server takes a job, like processing chunks for an upload, it marks it. If it dies, the job eventually times out and becomes available for another server to grab.
But how does the new server know where the old one left off?
The system needs idempotency. The processing steps, chunking, hashing, encrypting, uploading to S3, should be designed so that running them again on the same data doesn't cause harm. Because blocks have unique hashes, if a block was already successfully uploaded to S3 by the failed server, the new server can detect that, maybe by checking S3 or metadata, and skip it, only processing and uploading the missing blocks.
Got it. Avoids duplicating work or corrupting the file. What about the API servers? They were stateless, right?
Yep, that makes failure recovery easy. If an API server dies, the load balancer just stops sending traffic to it. Since it held no state, any other API server can handle the next request from the user without interruption. We just spin up a replacement server.
Okay, now the tricky one. The metadata database. What if the master database node fails? That sounds bad for strong consistency.
It's the most critical failure scenario. You need a clear failover plan. Typically, you have one or more slave nodes replicating data from the master in near real time. If the master fails, detected via health checks or monitoring.
You promote a slave.
Correct. An automated process promotes one of the up-to-date slaves to become the new master. This needs to happen quickly to minimize downtime, the recovery time objective, or RTO. Once the new master is active, other slaves connect to it, and a new replacement slave node is brought online to restore the desired level of redundancy.
Well, what if just a slave node fails? Less critical.
Much less critical, assuming you have more than one. Read requests that were going to the failed slave are simply redirected to another healthy slave. The system detects the failure and works on provisioning a replacement slave server to rebuild the replication set. Write operations, which only go to the master, are unaffected.
And the metadata cache, if a cache node dies.
Caches are usually distributed and replicated too. If one node fails, requests just go to other nodes holding replicas of that data. If the data isn't found in another replica, a cache miss, it just fetches it from the database again. The failed cache node is simply replaced.
Okay, seems like redundancy covers most things. What about the notification servers using long polling? You mentioned earlier that failure there could be slow to recover from. Why?
It's about the connection storm. If a notification server handling, say, 1 million long poll connections fails, all million clients instantly lose their connection.
And they all try to reconnect immediately.
Exactly. They detect the dropped connection and immediately try to establish a new long pole connection, likely hitting a different healthy notification server via the load balancer.
Why is establishing connections harder than maintaining them?
Establishing a new TCP/IP connection and handling the initial request, authentication, setting up the poll, involves more overhead, CPU, memory for state tracking, than just keeping an existing, mostly idle connection open. When 1 million clients try to do this simultaneously, it can temporarily overwhelm the connection handling capacity of the remaining servers, specifically things like the kernel's backlog queue for incoming connections.
So even though the servers can handle 1 million open connections eventually, they struggle to accept 1 million new ones all at once.
Right. It leads to a temporary backlog, connection timeouts, and a noticeable delay in users reestablishing their notification channel. Syncing feels slow for those affected users until the connection storm subsides.
Interesting bottleneck. Okay, finally, let's discuss a major design alternative mentioned in the sources. What if clients uploaded files directly to cloud storage, S3, bypassing the block servers entirely.
Yeah, it's a fundamental architectural choice. The big advantage seems obvious, potentially faster
Well,
uploads.
that fast.
You eliminate an intermediate network hop. The data goes client minus S3 instead of client mock server minus S3. Fewer hops, less latency, potentially higher throughput.
Sounds good. So why didn't the reference architecture likely choose that path? Why introduce the complexity of block servers?
Several significant drawbacks to the direct to S3 approach. First, engineering complexity on the client. All that crucial logic, chunking the file correctly, compressing it effectively, calculating delta syncs based on previous versions, and especially performing robust encryption would have to be implemented natively and perfectly on every single client platform.
iOS, Android, web, Windows, Mac.
Exactly. That's a massive development and maintenance burden. You're duplicating complex critical logic across many different code bases and teams, increasing the risk of bugs, inconsistencies, or sync errors specific to one platform.
That sounds like a nightmare to maintain. What's the other big drawback?
Security. If the client is responsible for encrypting the data before it leaves the device, you have to embed your encryption keys or key management logic within the client application.
And client apps can be reverse engineered or run on compromised devices.
Precisely. It makes your encryption far more vulnerable. A malicious actor could potentially extract keys or manipulate the encryption process. Centralizing the encryption and compression chunking logic on the server side, block servers within your controlled, hardened infrastructure is much more secure. You control the keys, you control the process before the data ever hits the multi-tenant cloud storage.
So the block server architecture trades maybe a slight upload speed gain for huge improvements in security, consistency across platforms, and dramatically reduce client-side engineering complexity and risk.
That's the trade-off, yes. And for a system where reliability and security are paramount, centralizing that critical processing logic on the server side via the block servers makes a lot of sense, even if it adds an extra hop. Hashtag tag outro.
What a journey through the nuts and bolts of cloud storage. It's clear designing something like Google Drive is this incredible balancing act.
Absolutely. You're constantly juggling competing demands. We saw how they achieve strong consistency using ACID databases and careful cache invalidation, even though it adds complexity.
Right, and how they fight for low network bandwidth using those block servers for compression and, crucially, delta sync.
And then ensuring fast sync speeds not just through raw power, but clever choices like using long polling for the notification service to manage resources efficiently at massive scale.
It really feels like an architecture where the harder path was often chosen for the sake of long-term durability and scalability.
Definitely. But looking ahead, the source material hints at one more potential evolution, a small change with big implications. They suggested moving the logic that detects if a client is online or offline
Which is currently kind of mixed into the notification service.
up into its own separate dedicated service, a presence service.
Okay, sounds like just reshuffling boxes on the architecture diagram. Why is that significant?
Because by making presence, knowing who is online right now its own standalone queryable service, it becomes a reusable building block for other applications across the entire organization, not just file sync.
Ah, so it's not just Drive that needs to know if I'm online. Google Chat needs to know. Google Docs needs to know.
Exactly. Suddenly, that presence information is centralized and easily consumable by any service that needs it. It transforms what was an internal detail of the sync system into a foundational piece of infrastructure for real-time features.
And remember, we specifically excluded real-time collaboration like Google Docs editing earlier.
Right. But if you have the standalone presence service, building those features becomes much simpler. The Docs application can just ask the presence service, hey, who else is currently online and looking at this document?
Instead of Docs having to build its own complex online-offline tracking system from scratch.
Right. Precisely. It unlocks collaborative potential. Knowing who is co-present in a document or a folder instantly enables features like seeing other people's cursors, real-time chat within the app, awareness indicators, all built on top of that simple modular presence service.
Wow. So a seemingly small architectural refactoring isolating presence could be the key enabler for all those complex real-time collaboration features we see today. It turns the sync system into a platform.
It really highlights how thoughtful modularity can pay off down the line, enabling future innovation you might not even foresee initially.
Something for you to think about, how breaking down systems into the right reusable components can fundamentally change what's possible.
The details matter, always.
And on that note, that's all we have time for in this deep dive. Thanks for joining us.
Thank you.